So this chapter now talks about applications of calculus to various areas such as physics, mechanics, etc., chemistry. And the goal is just to give you a little overview of how we could use calculus in physics here in this section 7.5. And I know that some people right away shut down when they hear words physics, or other students may right away get very happy. So then calculus with physics will be the sequence of courses for you after you take calculus 1, 2, and I think maybe 3. So anyways, there are various formulas that I think quite intuitive being utilized. So if you're trying to push something that weighs 20 pounds on a distance of 2 feet, then work that you do is 40. Well, they measure it in terms of some physical units, not gonna get it, but they say foot-pounds. Okay. But if you gonna, instead of 2 feet, move it twice farther, let's say 4 feet, that'd be twice more work to do, so that'd be 80 foot per pounds. So you make it twice farther, you do twice more work. I guess it's pretty intuitive, right? So the calculation of constant force. The use of calculus starts when you're using variable force, and that's the idea. So, because otherwise you just use this formula and you put in various numbers and you're done, and that's what the basics in physics is working. So, variable force. So, what happens then? Well, we're trying to approximate various variable forces with constant forces on each piece. So, we break this into n pieces. So, that's where the calculus starts. So, you have n segments. And then I can say Alex is x0 to xn, that's n and 1. Well, we have first segment x0 to x1, so that's ending points. And then second segment 2 ends at x2, so the last segment would be nth segment. Even though technically it doesn't matter to us if that's n segment, whose n is 10 or 20, it could be any number, right? In fact, what they do then is to make sure instead of n approaching to infinity, what they actually talking about is delta x that they trying to call here as norm of delta. I have no idea why they decided to bring this stuff from advanced calculus, such as a norm, but well, they did, and that's great, I guess. If you break your segment into equal pieces, you say there's n many of them. Like, for example, here looks like there are 5 intervals, n is equal to 5. So what's the difference with that norm? I know I'm talking about this, but since it's here, so it may not be equal pieces. It may be any pieces. So some pieces may be bigger, some pieces may be smaller. So norm here, so they put this double bars just for you to understand what this is, because I don't think you ever saw this in math textbooks. In this particular case, norm means the maximum piece goes to 0. The largest goes to 0, because smaller ones, they're smaller, they will go to 0 as well. So as long as largest goes to 0. Well, some people might argue saying, you know what, Alex, the reason they did it is because they say one piece will be standard, and then you keep breaking the rest more and more pieces, but the maximum is not coming to zero, maximum will stay the same. So you keep breaking, but into n pieces, and n may go to infinity, but the actual maximum will stay and does not go to zero. Maximum will be, let's say, 0.2, whatever. So it's not going to zero maximum, and that's why just the n approaching to infinity does not even actually tell us that this is going to be some type of finite result, not going to be approaching to our area, because that maximum also must be approaching to zero. So I guess that's the reason why they coming up with this norm. And back to ideas of calculus is because if you start to deal with some not very nice looking functions, like, well, for example, 1 over x, when your x is equal to 0 and your function is 1 over x, and if you're gonna use this interval, say 0.2 of the length, and the rest of interval you keep breaking and breaking and breaking into pieces, but that stays the same. But the function, the major issue is it will be up here on that interval that we are not cutting into. And that's why it's important that this one also goes to zero, not stays constant 0.2. See the idea that n approaching to infinity is usually not enough to say that we have everything integrable. That's the key idea here. But anyways, we don't encounter that. And in fact, to go over this, to say that you break it into equal pieces, and that's how they overcome it when function is continuous. When function is continuous and it's differentiable as well. If it's not differentiable, then various other things possible, and that's why this norm is appearing here to make sure that everything works. But anyways, I don't think you're ever going to see this unless you start taking more advanced math classes. So I'm kind of surprised to see. So anyways, so what they do now is they notice that the product of a force multiplied by the distance when force is constant, that gives you so-called work function that you need to do by moving something on a distance of d. And then since force now varies, well, then you break this into pieces of force and you end up with a work that is turn out to be integral from starter point to end point. And this force we integrate with respect to x, so it'll be f of x dx. So analogy, but now force is not going to be constant f. That's why we need to put integral. You can apply integral to constant force as well, but that's, I guess, going to be same as just multiplying it by the constant. That's why it's not much interesting. So point is, it gives us ability to do a little extra, a little more stuff with our functions that vary applying our function calculus. So I want to look at, let's say, Hooke's law. Now, there are various laws of physics that we, again, can intuitively feel that they work, but again, my goal is not to get into physics, and that's why I will just briefly discuss this, do a couple of examples, just go over already examples in this section and see that using calculus does make sense in this whole setting, because otherwise you would probably not able to do this exercise. So anyways, looks like they give you initial conditions for this so-called Hooke's law. They say that if you have force 750 pounds compresses spring 3 inches. So in this formulas, you put 750 in this particular formula. The coefficient is K, coefficient that stays constant, some kind of particular constant, K, that we put 3 instead of D, and that way we can see that constant should be 250, right? 3 times 250 is our 750. So that's there straightforward. I'm sure you did it if you took basic physics class. And then 250 you put back in the formula. I think we even did this when we had intermediate algebra a while ago. So now you have a function of x, f of x, that we produced. So now that's what I'm going to integrate, and they give me some more information. So now I read further. So it says, find the work done by compressing the spring extra 3 inches. What does that mean? Extra 3 inches. So we already started at 3. So we already compressed the spring. They try to draw here. So the spring is compressed, but you want to compress it more. So from 3 extra 3, that'd be 6, right? 3 plus 3 is 6. So now your function that you want to integrate is 250 times x, right? And then you put dx. Integrate with respect to x variable, just like that. So calculus-wise, it's really very, very straightforward, right? This integral is very basic, and I'm sure you'll do nothing but enjoy taking it, right? So 3 to 6. So now I cancel by 2, I get 125. And then the upper limit I plug instead of x, so that will be 6 squared minus lower limit is 3 squared, and that way we can see that. From 18, I subtract 9, it'd be 9, and 9 multiplied by 125 is what? That's 3375, I guess. That's the already calculated. Okay. Right. So that's x squared. I have to 6 squared. 36 minus 9. No, 36 minus 9 is not 9. 36 minus 9 is going to be 27, right? So 27 times 125 is 3375. So I can put this in the calculator and get it. So calculus-wise, it's nothing, but it is interesting application of physics, right? So there's one of those. So there are various examples. There are other laws, and I think interesting is here lifting the chain. So that's something that will give a little bit appreciation of what we're doing. So how much work is going to be done by that piece of equipment? So let us see what they're talking about here. So we have interesting start. Let me get some room here on the side. So they say 20-foot chain is weighing 5 pounds per foot, and they trying to lift the whole thing. So please notice this lifting process will make you apply different type of force, because, for example, if you lift first piece of this chain to that height, it will give you a little bit of work. But then next piece, when it's added, your weight is doubled. And next piece is doubled, but you're not lifting this piece higher. So what they do is they say, let's calculate the force to raise piece of some small weight, but it depends on Y. So the height that we're lifting, so if whole chain is lifted, then this piece is lifted by that height, but first piece is lifted much higher. See, it varies, so work varies. So our Y's will vary, and that's the idea. So they say the amount of work, since the chain weighs 5 pounds per foot, will be multiplying. So of course, we'll be multiplying the amount of work of weight by, so that's little delta Y by 5 pounds per foot. So that's work that we are doing with that little piece. But then we also have to lift it by Y units height. So we need to multiply that 5 delta Y's, that one piece, by Y. You can put Y in front. And so that's for this piece. And for the other piece and for the other, that's why it's a sum, and take a limit when number of pieces goes to infinity, and that's where we get integral. So limit of sum, and we actually start at 0 and end at 20, right? They say here 20-foot chain until it lifted all the way and one lowest end just touches the ground. So we end up with integrating phi y dy. And once this explanation has been accepted, we can finish up with doing calculus. And doing calculus, we're just taking antiderivative and it's all done here. So once again, from perspectives of calculus, these problems are pretty straightforward. They're like very basic and nice. But from perspectives of physics, it's definitely something that worth to think of. But this is not physics class. That's why I don't want you to, as I said, shut down and panic and say, oh, no, whatever. So, no, don't worry. I'm not going to test you on that. My goal is just to introduce you with this ideas. So we take little piece and bring it up by some particular value of y because it varies. So not by entire 20, but by y. So that's the idea. And this brings us to so-called mechanics portion that continues dealing with those so-called momentums and stuff. So I can go to another idea that you probably encountered before. Let me maybe clean the mess. Stop sharing. Share it again. In the next section, they use analogous formula to what we saw. So we take momentum times x. So how can you, I guess, intuitively see it? So if you have two people taking the swing, how to put it in equilibrium position? So let's say one person is weighing, one kid weighs 40 pounds, and the other weighs only 20. So how can they be in equilibrium? Well, in equilibrium they can get when the products, let's say, put one 20 feet away from the center, so that one should be 40 feet away, twice further. So that way, on one side, 20 times 40 will be the same as on the other side, 40 times 20. Right? So both will be 800, so they will be. So if one kid weighs twice more, you should put him twice closer to the equilibrium, and the one that weighs twice less will be twice farther to compensate that. In other words, we have weight. So what letters they use? Like mass. Okay, mass of one multiplied by the distance of one on one side will be the same as if you take mass of the second multiplied by the distance of the second, which is, if you start to think, what else can this be? So that's for two, but what if you have lots of them? Lots of them. So again, equilibrium, usually you say it's X bar to tell it apart from all those various weights. And to get to zero, we need to get differences xi's subtract that coordinate of equilibrium times mass times mi. So mi is in front. Okay. And that has to be equal to zero. So it stays put, so it does not move, right? And that I varies from 1 to n. So it could be any finite number of these weights, and that's what we can now do by a little bit of algebra. So I can go mi's times xi's, subtract the sum of mi's times x bar. So I want to find that position for the equilibrium. So where should I put my so-called fulcrums? So it says it stays in the balance. So how can I do that? Well, since the goal is to have this equation work, I can bring this on the other side and then end up with finding position mi, mass, position of x bar. So it's still mi times x bar. So how to find x bar? Well, divide it by the sum of mi's, because x bar is constant, so I can factor it out. Oops. So I can now divide by that sum of mi's both sides. So that way I find that balancing position. So it'd be the sum of mi's multiplied by xi, and this is over sum of all mass. And please notice that sum of all masses we can call as a mass of entire system. So there's a capital M, the mass of all of these weights on one side and on the other side, and this will be divided into the sum of each mass times the distance of mass. So that's the formula that they coming up with for the x coordinate. Turns out it could be extended into, so they do this little algebra here, same thing, and then they come up with a formula for the, so sum of all of these guys, they introduce another letter, what for, so this is already sum of them divided by total mass. And if it's in two dimensions, what's interesting is now we can extend it to two dimensions, and analogous will be the formula if you are dealing with x coordinate as well as y coordinate. So x coordinate and y coordinate. Please notice that one needs to be careful that m index y is for finding x coordinate and m index x is for finding y coordinate of the center. And I say, oh, that's pretty interesting. Well, that's worth to think about, but again, you just put a picture and you see exactly right away why this will be the case. But once again, my goal is not to get into it, but to give you an idea that since we are again using calculus because it all varies, so they say there could be variable mass for the pieces. or variable distances for the pieces, then they will be using integral. So whenever they have a sum, so they will be having analog of integral, and that will be delta x, so that'd be dx. So that's the one that we're again seeing down below. So they have it? Not yet. Okay. So anyways, they will have it after. So this all comes to three-dimensional situations, and the last thing I wanted to show you is how to deal with so-called planar lamina. So it's like a uniform thickness piece of metal. So they made a nice picture on the bottom. So if we have two functions, f and g, both of variable x. So here's your x-axis, and of course y-axis is with perpendicular, right? Y-axis. So they have a piece of uniform thickness. That's what they call as lamina. So it's a plate, and thickness is uniform. So they find the mass of this lamina, and that's usually density times the volume, right? But if volume is thickness times height, that's the area of cross section times height. They say if we take the area of cross section, it's uniform. So the thickness will be, say, 1 for convenience. So they put not volume, but they put area. So they treat the thickness, which is not variable. But later they can extend it to one more step, but that'd be double integration. So that'd be too much already. So that's what you're probably going to see in Calculus 3 if instructor is into physics. But I don't think we'll see it here. So anyways, so mass is density times instead of volume is area. And how do we find the area? Well, looks like to get the area, we need to subtract from upper the lower function, right? F subtract g. We already saw this, upper minus lower. And if we integrate with respect to x, and we start at a usually and end at b. For convenience, we always use same letters, a to b. So that's what we call this area of this region. And now we're going to try to find center of mass. So here's one thing to watch out, because for the center of mass, we have two coordinates, right? X bar and one y bar. And now to be able to get it there, I need to realize that, so I can find the mass of this, and that will be already analog of my denominator. And to get to numerator part, I need to go to the coordinates of this point. So on the x, in terms of x, the value will be just x bar. But for the y is different. Notice for y coordinate, when I need y bar, is going to be a half of sum. So if I take the coordinates such as f and g, and I'm going to have to add them and divide by 2. Average value. That's another thing to realize. So whatever is here, whatever is there, I have to add those and find what's in the middle, so divide by 2. Again, because the lamina is of uniform thickness. And that way we'll be able to find the area of rectangle. So just one, we cut it into n pieces, so that'd be area of one rectangle, and then we'll add all of these areas together, and that's how we get the integral. And again, the integral will go from A to B. And then we're gonna produce the actual formulas that they nicely provide us in here. So the mx. So for mx. Notice that this is my y coordinate. Remember, I just said that we have to take the y coordinate for mx and x coordinate for my. So it's switched. So we get the average of these two guys, f of x plus g of x over 2. So we're multiplying y by f minus g and integrate with respect to x. And for my, I'm writing my, we have integral from, again, a to b, but now it's, instead of f plus g, we taking just x, and that's f minus g. So I'm just trying to give a little bit of intuition into these formulas, otherwise they're just very foreign, looks like. And that way we get a center of mass. So coordinates here, I need to also divide by the m, which is my actual integral that we already saw out there, by that mass of the whole thing, of the whole lamina. And that's how I found. So what do I find? Center of mass. So it's not for the line, but the two-dimensional plane. So what's the center of mass of that plate, of that lamina? Well, I need to divide by the total mass. So total mass of that thing, and that lamina, my mx and my. And that's what they have here. So again, to get mx, I need to divide my. So for the x coordinate, I divide my. You see, I want to say why my as well. That's the interesting thing to think about. And for the y coordinate of that center, it's coming from this construction. I divide mx. So once you have formulas in the calculus kicks in, and for calculus purpose, all we care about is just plug in numbers and get it all calculated. So I'll do one problem and then I'll end with this rest of chapter, just formally to show you that we can use calculus in various areas of life, such as in physics and in mechanics here. So I can take a look at example for how to trace. Well, first of all, I need to find the mass of that lamina that they produced using parabola. So it's cut by the x-axis. So this is my lamina. So my lower function g becomes 0, so it makes life easier for them. So just function f of x that we integrate them, which is nicer. So you find antiderivative, and then you multiply it by density. Please notice that density factor will always cancel because it will be with mass, the density, and then with center is also that so-called rho, so it will be also canceled, and because it's on the top and on the bottom, so it will disappear. So we don't care what density of that particular material is for the calculus purposes, so we just don't care. So I just integrate that and get some result, and that will be my denominator. And now for y coordinate. So for y coordinate, I have to take this function So how do I get y coordinate? I need to take f plus g over 2, right? So to get mx, please notice that g is 0. See, they decided for convenience in the first example, we'll get something nice. So we subtract from our function 4 minus x squared, 0. So we subtract nothing, which makes life easier, dx. So that's 4 plus x over 2, 4 minus x over 2. But we also need to multiply it by f minus g factor. That was very. So what's the f minus g factor? Well, this will be another same exact 4 minus x squared, and then minus g minus 0. Because again, the lower function is 0, so that is nice. And once it's set up, notice we go from minus to plus 2, our integration, right? Minus 2 to plus 2, and you get something here when you integrate. So basically, you have that one over 2, sorry, over 2. You see y over 2, well, because of denominator over 2. So need to be careful. So then you multiply these two parentheses and distribute and integrate, and you get your y or x coordinate, which is 256 rho over 15. So just copy. I don't want to do that arithmetic. I'm sure you know already better than I how to do this, right? So that's great. So this will again enable us to find the x coordinate. So it's mx, oh, sorry, y coordinate of that center. And they even put it here on the y-axis. For some reason, they decided to go three-dimensional space. And notice they say that it is on the y-axis. So if you try to find the x coordinate, so you need to get my. Let me set it up, and you will see that this has to be 0. They don't even bother to do it. In fact, they just said, find the center of mass of uniform. Oh, about x-axis. So to find it about x-axis. So they found it about x-axis. And if you're looking for the center about y-axis, now you go with multiplying by x, your, again, difference f and g, which is 4 minus x squared, and subtract 0, right? And then dx. And what you have here as an integrand will be 4x, and then when we multiply by x squared, that'd be minus x cubed. Please notice you're integrating odd function from minus 2 to 2. Remember, you don't need to waste time anymore. Odd function means it's symmetric to the origin, like cubic function is example. And from minus 2 to plus 2, this here is the same as the one below, but the odd function means they're same but opposite in sign, so this integral is 0. Or if you want, you can continue with integrating, and eventually we'll see, because at positive 2, notice it'd be x squared over 2x to the 4th over 4. They both even powers, so you'll have to subtract from upper the lower. You will have same numbers to subtract, and that's why the integral is 0, and that's why the coordinate for y, your x coordinate will come as a 0 or whatever it was, m, which is 32, or whatever you put into 0 will give you 0, as long as it is not 0, right, on the bottom. So that way, x coordinate is 0. which is very nice. Nice for starters, and that's going to be our finish as well. So they found that this point of x coordinate is 0. That's what we just saw. Because it's on the y-axis. And you can intuitively see it, because if you're trying to see center of mass of that figure, then notice it has to be somewhere along y-axis so it stays without falling, because if you move it someplace off, it will fall the opposite direction, right? So it has to be in the middle of that figure. So its x coordinate needs to be 0. So x-axis 0. So anyways, these are interesting, but I would say from calculus point of view, it's kind of waste of time, because all you do is use the power rule for antiderivatives, and this is not really what we have as objective of calculus 2. Power rule was considered in calculus 1. I don't want to move on to the next section, just to give you a brief idea of what that section is talking about. So that's the one. It's actually next chapter. So fluid dynamics, there's more stuff, of course, but again, we don't worry about this. That's ending our chapter 7, and think it's enough of it already, right? It's been too much time we spent. So next time we'll start with substitution. Let me clear the mess. And I'm sure you already saw substitution when you take antiderivative, right? And it's enjoyable kind of stuff. So we'll have all types of substitutions. And that's going to be our plan for Thursday. I think it's a good moment to stop with this physics, mechanics story. Again, it's for general knowledge, so I'm not going to worry about this on the exam. So I'm going to stop recording.